I have a degree in mathematics and statistics, but I teach a lot of introductory stat classes, and I can tell students are very confused about what's the difference between these two. And I can tell that this is a confusion when I hear, "Oh, I'm really nervous to take this class because I struggled in calculus," or else, "I just wanted to thank you for teaching this class because this was the first math class where I feel like I understood what was going on." And the problem is, students have this idea of the relationship, that math includes a whole lot of things, including the subset of statistics, which is like mostly algebra, even some calculus, and it's just math applied to the real world. But that's wrong. The picture does include some math. Not really a whole lot, but enough for what we need. But statistics also includes some psychology as you work with the client. What does random mean to you? When you did the survey, were you standing or sitting? That might matter. And you have to be able to teach the client why that matters. They don't just want the answer, they want to understand the implications, which means you're going to need to be able to explain clearly what these complex things mean in such a way that anyone can understand it, so that you can make a plan for how to move forward and make a decision that's going to get you where you want to be, whether it's a policy change or a grant or a research paper. And in order to do that, you're going to have to understand the subject matter of the client. If your client's an engineer, you'll need to know their terms and definitions. You'll need to understand how do geneticists write papers. It's different for every single field. And once you know what the question is, that's when you can actually put the data in the computer and run the analysis. And you'll notice I put computer science right next to math because a lot of statisticians aren't really that great at math, but they leverage that by knowing how to ask the computer to do the math for them. So if you want to be a statistician, you're going to need some math skills, but you're going to need skills in a lot of these other areas as well. And I might note that while math and statistics are often combined in departments, statistics can be combined with a lot of other departments because there's so many skill sets that are shared. And then there's this middle part, which is unique to statisticians, which is the breadth of scientific research, BOSS, because statisticians are the boss. Get it? What I'm trying to say is everybody does research, but they don't get the exact answers they were hoping. There's uncertainty, there's error. And as they try to model that error, there's millions of options. If you don't believe me, open up any statistical software package. And how do you know what to do when there isn't a single correct model that is the right answer? So a statistician has to have an open mind of all the possibilities, along with the experience to say, here's the right thing to do in this case. So let's break down some of the main differences between these two sciences. Mathematics would start with some assumptions and models, and based on that, we're going to try to solve the various pieces of this model. With statistics, you need to talk to the client, understand their goal, and from there, create what you think is the best model. Math would be looking at these assumptions to say, here is the equation which gives us the answer. While statistics says there's a lot of solutions here, and there might be more than one answer. Mathematics isn't going to be facing ethical dilemmas because based on the assumptions, this is the model, these are the equations, there's the answer. For statistics, there's constantly this moral dilemma of which one is slightly better given the context based on my judgment. And that's why in mathematics, everyone's going to agree on the answer based on the initial assumptions. This is what it works out to be. For statistics, there could be several correct answers. And you look at the client's goal, what are they trying to answer? What's their paradigm for understanding the world? Okay, within all these models, here's the one I think we should go with because it helps you answer that question. So a math teacher is going to be emphasizing logic, starting with the assumptions step by step. Can you do each step correctly and put it all together to come up with the answer? A statistician is going to be teaching skepticism. Can you look at the decisions and the judgment calls of other people? Are they being naive? Can we put all these pieces together to say we believe this to be true even if there isn't proof but the data suggests that it is true? That's how science moves forward. It won't be surprising that the foundation for learning mathematics is based off some of the great scientists through history, Pythagoras and Euclid, stuff that was developed a long time ago because it was right then and it's still right now. For statistics, technology changes what can be done. Thanks to computers, we can do bootstrapping and jackknife techniques that weren't feasible before. So rather than compare the two this way, I want to show you my introductory stat class broken out into what's statistical and what's mathematical. At the very beginning, we do teach how do you calculate average and standard deviation, but we're more interested in can you understand what we mean when we say that statistics have uncertainty. Calculating probabilities is certainly part of a stat class, but really being able to define what does it mean for something to be unusual. The reason we're using that is because when we get to the normal distribution, we're going to talk about how far are you based on the error. That's, again, defining unusual. For the sampling distribution, the only difference is we're going to add that square root of n. But we're talking about errors for a group instead of just errors for a single individual. And that helps us to be able to talk about how accurate those statistics are. That way, chapter 5, which in some ways we call this our first actual statistical chapter, we want to use probability to make decisions. That's the whole goal of the class. And we want to be able to understand that when you make a decision, you could make an error, and there are lots of different kinds of errors that could happen. A confidence interval, mathematically, it's the same equation, you're just solving it backwards. That's not the hard part of chapter 6. What's hard is being able to understand, what does confidence mean? We're talking about certainty of parameters, but we're not using probability because after the confidence interval is done, it doesn't have randomness anymore. That's a hard concept for students to get. When we go to chapter 7, we start doing the t-tests. Mathematically, all we're doing is we're switching z with t. But understanding what it means to have an error in the errors, that's a big deal. Combining variances between groups, talking about the larger uncertainty of t, what makes t different than z, those are big steps. And often I will see students who are really good at the math parts, but they're missing these ones, and they don't do well in the class. It's not the equations that trip people up. Proportions, we switch x bar for p hat. It's actually mathematically easier because we're going to connect the variance to the average. But knowing how to handle those categorical results, that's a big step. From chapter 9, there really isn't any math, but we're talking about data collection, bias, lurking variables. It's not an issue of can we use the numbers, it's how much do we trust the numbers. Tell me the story behind each of these numbers. That's statistics. For the chi-square test of independence, you get those by multiplying probabilities. That's a math trick. But understanding that independent data is different than talking about independent variables. And for the chi-square goodness of fit, it's the exact same math. But then we emphasize that we're talking about a ratio from errors to differences. This, what you got minus what you expected divided by the error, that's the same equation as this guy up here. It's a generalization of it. Can you understand what this equation has the potential to do? I will often tell my students, there's really only this one mathematical equation in the whole class, and then we have slight variations on it. Students who see that pattern start to understand all of statistics and how it all works and how it all connects together. Students who focus on the math feel like there's 12 different equations and they can't keep them all straight. For regression, that linear equation is something they've seen in algebra, which is a prerequisite for the class. But we're going to talk about the residuals, the correlation, linear changes, how to do predictions, how do you use that in order to make decisions about science and about the world. So let me emphasize something important here. There is math in the introductory class, but it's pretty simple. And really from this one idea in chapter 3, the rest of the class is alterations to this one equation. So if you're good at math, that doesn't mean you're going to do well in this class unless you also learn these concepts and understand them. If you're afraid of math, don't worry, you can pick this stuff up pretty easy. Focus on these things and you will understand what a statistician does that's different than what a mathematician does. And let me illustrate with a day in the life of a statistician. It's not at all unusual to have someone stick their head in my office. Hey, I was doing a study on whether monkeys can swim through chocolate pudding easier than custard. Do you think you could help me for just 30 seconds? You're studying what? Okay, look, what you just described is a two-sample t-test. Here's the equation. That's math. But in order to use this equation, we assume there's normality. Now, nothing is ever perfectly normally distributed, but is it close enough? Is it going to give us good enough answers? Could this data use that? That's ethics. But in order to make that kind of judgment call, we're going to need to talk about the terms you're using. How did you conduct this experiment? What are you trying to answer? And how accurate does that answer need to be? Oh, well, I'm building on this research from this other university where they used an error rate of 8%. Okay, well, it's pretty clear we're going to need to schedule some consulting sessions so we can talk about it. And I'm going to be thinking about the different options, other types of tests that we could use in this scenario. And in order to know the names of these different tests, let alone the subtle differences in which one gives you better answers under which scenario, that's professionalism, which is why it takes a long time to get a statistics degree. But even knowing which ones are options, I still have to have the experience to decide which one is going to be the best. And I don't just mean a few minutes or days of study. It takes years of looking at models to be able to figure out which one is going to be the right one to do. Oh, gee, I thought this was going to be a quick question. So are you willing to help me? Yeah, come in and sit down, because service is at the heart of what makes a statistician love his job. So if you want to be a statistician, you'll learn a little bit of math and a lot of other things as well, and it's going to be one of the most enjoyable professions you could ever look into. Now, what are you doing to these monkeys?